So we are starting the first tutorial session in the morning with the learning-based control fundamentals and recent advances. Aditya Mahajan from McGill and myself, Silviu Niculescu from CNRS France. We are organizing it. And we have 5 talks today. The first one will be more or less an introductory one, and after you have 4 other talks which are devoted to some particular topics. The first question that we can have in such a context is why a new tutorial session and why on such subject? So there are a few things that for us we found that are interesting. The first one is that we are in a really growing, fast-growing research area. And when you're talking a fast-growing research area, there are a few fundamental things. One of them is just to see exactly what is interesting, what is new, and what are the directions to go for. And the second interesting thing is perhaps there are ideas that it will be interesting to develop at the interface between the new research topics and more or less former or older research topics, including also control. And when we are talking about artificial intelligence and control, one of the important things is that there are a lot of connections in the past, and for a particular reason, we decided just to stay for the period between 1950s and 1974. Why 1974? Because if we are in 2024, it's a question of 50 years. This is the first point. And the second point is just because on the left and on the right, if there is a kind of connection between, the connection should be in both directions. So we think that there are ideas developed in artificial intelligence that are useful for us, and also there are ideas coming from control area that perhaps are useful in artificial intelligence. And in general, when we're talking about something which is at the interface, interesting things happen on the interface. We are not talking about interdisciplinary for the moment. We are just saying interesting things happen at the intersection. And the idea is just to see exactly what are the things on the intersection. So introduction. Once again, it's high level, so we are entering in a few details, a few basic ideas in learning, but with a control flavor point of view. So we are not talking learning from the computer science point of view, but just from the control point of view. Motivation, examples, and terminology. In terms of example, we start with an extremely simple example. I will not enter in all the details. Why? Because it's extremely simple. It's a first order example, is a scalar case. We have the controllability properties. It's just to introduce the notions. And after, we are going through the terminology and we're arriving to learning in stochastic system, and in particular, Markov decision process. And we'll try to switch when we're arriving on Markov decision process with Aditya, and Aditya will present this part. And I will come at the end, after learning in MDPs, what are the topics not covered. For sure, we are not talking about delay today, or at least a little bit at the end. So I've said why a tutorial and what we are including in saying in this first part. So the background and terminology, and in particular the Markov decision process, will explain the link between Markov decision process and reinforcement learning, some fundamental ideas in reinforcement learning, and of course, what are the topics in the topics of the tutorial, mainly the other talks, and the way these topics fit in a larger context. I think this is quite important. Our colleagues will just figure out better than me, at least with respect to their own topics, what is interesting, and of course, a few insights in the topics not covered. So now, for the tutorial talks, I will not enter into the details. You have the program, information, theoretic lower bounds. We'll discuss about regret, what is the exact meaning of the regret, and the quality of, let's say, of an algorithm, and so on. Towards understanding cost-driven representation, learning and control. When we're talking about representation is in general something belonging to us. Of course, everybody is representing things, so we will have a look on about representation learning for control. Linear programming approach for data-driven control. So there will be an insights with respect to that. And at the end, inverse reinforcement learning. So let's go with a few basic ideas. So it's a bit strange, but since I said that we are staying in the period between 50 and 74, we decided, and it was a common agreement between the speakers, just to go to science fiction, but only for fun. And what is interesting in science fiction, but it's starting from the 50s, we have a kind of obsession, at least in the literature, just to think about what are the goals of machine imitating and even going faster or better than the humans. So if we try to put some order in all this literature, and I mentioned only one guy, Philip K. Dick, and the reason for mentioning is he was extremely sensitive to the fact that the way the technology is affecting from one point the psychology and for the other point the philosophy of the human being. So 4 goals, to be honest. So learning and adaptation, there is a particular reason for which I connected learning and adaptation, because we'll see that in the past, learning is adaptation and adaptation is learning. Although these notions are completely distinct. Self-organizing and self-repairing. So now if we are entering a little bit into details, when we're talking about learning system ability, in fact, if you try to simplify at maximum, we have 3 ingredients. On the left, we have what we are calling the system, and saying the system is learning, the learning system. And on the other hand, we have the environment, and between these 2 things, we have the interaction. Now, when we're talking about this, of course, what we need is just to say something about what is the environment, and to be a little bit more precise what kind of environment we are talking about. And we are talking about interactions, what doing for? So we can see the interaction at several levels, but saying when we're talking about learning system, the interaction with the environment, there is a goal at the end, is just to improve something. This improving can be in terms of behavior, future behavior, or performance, but always is in terms of, we try to define a sequence between past, present, and future. So this is a schematic, a very simplified representation, so 3 items: system, environment, and interactions. Now, if we enter into details, so with respect to the environment, okay, there are several ways to think about it. It can be generic, it can be restricted, and what is important, it can be static and dynamic. When we are talking about reinforcement learning, it will be more precisely a dynamic environment. We'll come later on this. And we are talking about interactions. Of course, for a guy coming from control, it appears natural. This interaction is in continuous time, or it's a sequence of interaction, or it's a discrete time, but in this sequence, there is an order. We're starting from the left, and we're arriving to the right, left being past, and right being future. And now we are talking about behavior. As you see on the slides, there are several levels. In general, qualitative and quantitative as a measures, because trying to put some order or try to understand in concept, the easiest thing is just to have a mathematical representation of what we wish. The simplest one is measuring, and what we are for measuring. If we're talking about the qualitative, it's an added value of the knowledge, how we are interpreting this new knowledge, or how we are constructing this new knowledge. And if we are quantitative, we are talking about parameters in general, and we are talking about parameters. We'll have in particular parameter learning in functional equation, and this is more or less the Bellman optimality principle. Optimizing indices, this is more or less, we can say, in a schematic way, in a simplistic way, we are talking about optimal control, but we can have also a logical sequence of conditions and actions. Now, learning as a process, this is another long story, and I try to simplify it at maximum in a very simple way, in the sense that when we're talking about reasoning, there are mainly 3 ways to. Of course, if you need the slides, do not worry. I will send a slide to everybody who wishes. There are 3 ways to reasoning. The standard one, or the simplest one, is the so-called supervised reasoning or supervised learning, in which we are constructing a deductive reasoning. The classical ways, when you are going to school, you have an instructor, and you are getting the information by a very by a simplistic logical construction by using an organized knowledge. And the opposite thing, you have the inductive reasoning, and the classical example is more or less from examples. It can be at one trial or incremental trials from, in general, partially learned concepts, but it can be also from observation and experimentation. And between these 2 things, there are the so-called reasoning by analogy or similarity. There is an excellent book, which is Mathematics and Plausible Reasoning, which was written, the book was written by George Polya in the 54, and I'm just recommending to have a look to this book. He is focusing more on the analogy and similarity and also inductive reasoning by saying that this is more or less a driver of the future development in mathematics. Now, reasoning by analogy and similarity is a bit more complicated in the sense that we are trying to transform some knowledge from one field, from one area to another area. But in general, when you are constructing such a mapping from the left to the right, we are mainly mapping the relation between things and not necessarily the added value of the new knowledge in the new domain. So this is extremely important because we need a particular verification procedure in order to have a kind of guarantee of if there is a new knowledge in the related area domain, that this new knowledge has a real added value. But on the other hand, this is a useful way to interpret or to understand things by using such kind of findings. It was developed in the psychology at the beginning, and you have the notion of mapping in psychology since the 50s, and it arrived also in the case of, let's say, computer science and learning. Now, surprisingly, when we tried to find, saying, the first references, and in terms of overview, we arrived at the first reference in overview in learning control system review and outlook was published in the 70s in IEEE transaction automatic control. And for fun, the same paper was published in '86 in another IEEE transaction, which is pattern analysis and machine intelligence. And King Sun Fu, he is the guy who is at the origin of this IEEE transaction, let's say, new transaction starting in the 70s. And what is interesting, you see exactly at the first view that the problem of learning is strongly connected with what we know in the control literature, which is a problem of estimation, or in some sense successive approximation. Please read what he was saying. And he is connecting this with the controller. So I'm simply recommending that you are taking a look to this interesting paper. It's available. It's available for free. You do not need to have any kind of IEEE account. And now there are 5 learning schemes. And these 5 learning schemes, he mentioned more or less the publication before the 70s. And he's mentioning trainable controllers using pattern classifiers. So he was a specialist in pattern analysis and classification, a reinforcement learning control system, Bayesian estimation, stochastic approximation will be a little bit later on stochastic approximation and stochastic automata models. So now, I mentioned at the beginning learning and adaptation. I've said that learning and adaptation is learning. So what is interesting and is important is that I mentioned here also Umberto Eco, and in particular the so-called common cultural codes in semiotics. I will not enter in any details in semiotics. I'm not a specialist in semiotics, but reading Eco, I found something extremely interesting. When he talks about signs, he associated to the notion of sign a function. And what is nice is that for him, this function it represents something related to some dynamics. So now, in order to translate this simple in our context, is that each generation uses more or less a particular way to name things. And when we are moving from one generation to another, the same thing will have a different concept. So think about a cellular phone. Cellular phone for our grandparents has no significance. Of course, for our future kids and so on, our future nephews, perhaps it will be something extremely different. And this is the case for learning and adaptation. So the beginning learning and adaptation was more or less the same thing of 2 distinct issues. And what is important in this particular case is both things are related and linked to environment. We cannot talk about learning and adaptation without talking about the environment. And of course, I've just said that, I was just saying here, written here, that adaptation is fairly close to, let's say, to the feedback concept, and in fact, monitoring performances by adjusting parameters. Now, learning and adaptation, in order to make it more consistent with respect to the idea learning and adaptation are more or less the same thing. So we decided decided to make a choice with one of the paper of Bellman and Calaba, and you see here 3 statements which are more or less in this paper, in which you have on the one hand decision-making device, on the second hand uncertainty. Uncertainty means that the model is not perfectly known, and when we have a model not perfectly known, we have a large amount of ways to represent or to think it or to interpret and to handle it. And after you see on the second statement that learning and adapt are more or less on the same level. And finally, that this paper mentions that automata and machines that learn, more or less. And now, other references, this time is from IFAC proceedings. It was 73, let's say, a paper that it was a kind of tutorial paper from one hand, and on the other hand, it was a plenary talk. It was adaptive system theory today and tomorrow. And as you see, Zipkin was simply mentioning that learning and adaptive are more or less learning system or adaptive systems are more or less the same thing. Now, of course, things are a bit more complicated, but we are still trying to simplify. And in general, when talking about learning, we are talking about multi-stage decision problem. And the idea is that Bellman, of course, with his students, collaborator, just proposed a unified framework based on dynamic programming. And the idea of the dynamic programming is just starting from a problem, just to define some sub-problems, to analyze separately each individual sub-problems, and to due to the structure of the sub-problems, we are able to conclude for the overall problem. Of course, there are limitations with respect to that, and the classical limitations are in terms of time and spatial complexity, but also to the idea that when we are defining sub-problems, we need to pay attention to the overlapping of the sub-problems. If there is a strong overlapping at that moment, it will have some difficulties in order to converge. And what is interesting, in this early period, that the adaptive system was interpreted, was seen, at least in terms of the literature that I mentioned, as a multi-stage decision problem with no complete information. And now, Zipkin, he used the concept of stochastic approximation that it was developed by Robbins and Monroe in 1951. And what is interesting that through Robbins and Monroe, their stochastic approximation approach was developed outside from the control. The ODE, ordinary differential method, published in the 70s, 72, if I remember well, was proposed by Jung, who is a known researcher and professor coming from Sweden. So parameter choice and convergence result based on average risk optimization, an adaptive system was relying on iterative learning algorithms. So, for the terminology, the policy is nothing else than a decision of a sequence of decision rules, and optimal policy is the most appropriate, the most advantageous policy in respect to some criteria that we define in advance. So the principle of optimality is exactly what I was saying, and this is exactly taken from the paper of Bellman in 1954. The idea to divide the problem in sub-problems, and with respect to each sub-problems, we are solving the sub-problems, and we are concluding with respect to the overall problem. So now the Scala example, I will go extremely fast. But I have said you'll have access to the slides. We have here a controllable system, the dynamical one, which is extremely simple with alpha, which is a real parameter we assume, which is different from 0, but it's only for simplifying the things. And in this particular case, since it's controllability, we can go in any direction, of course, in the real space. And we define a cost function, which is a criterion, which is nothing else than a quadratic criterion. So there are several methods in order to figure out how to solve it. And the standard L-cube problem is just finding the sequence of laws, we are in discrete time, which are minimizing the cost function that we are defining, we define above. In this particular case, since we know x0, and if we have the whole sequence u0, u1 till u tf1 minus 1, we can simply and directly construct the state of the system at a given moment by including the past control laws and the initial state. So from this point of view, the problem to be solved in this case is extremely simple, and we are simply depending on the control sequence that we are including, and is nothing else than just inverting a matrix. But if we apply the Bellman optimality principle, the idea is that, once again, the decision problem is interpreted as a multi-stage problem, and we are carrying out backwards in time. So we are starting with the fact that we know the final state, and based on the final state, we are going step by step to the first state in such a way that we are getting exactly the optimality. So optimality in this particular case, using the notation that you see there, xti is some intermediate state between 0 and tf being the final time. So in this particular case, V0, X0 is nothing else than the minimum LQ cost. So the computations are quite simple, and the dynamic programming principle is just, I mentioned that there is a functional equation. You see the functional equation, which is equation number 4, and we can rewrite this as equation number 5, because eta, in the way it is defined, will not depend on the corresponding input, which is the previous one. So there are some assumptions to be taken into account, and we are computing PT, which is nothing else than a matrix in the general case, by decreasing the time, so in backward in time, and we are getting standard way to represent this is just a simple computation in this particular case, and each k in kt will be the optimal gain and the optimal control law for the time t, which is defined once again backward from tf-1 to tf-2 and so on, just arriving to 0 and to arriving to the optimal sequence. So now, of course, this can be generalized. I will not lose time on that, and we are arriving to something that you already know. I will not discuss about the Pontryagin principle, the Pontryagin optimization principle, because this is a little bit out of the scope of this, let's say, of this lecture, and it will be too complicated to make it extremely condensed. And what I am saying that in the general case for the LQ problem, for the infinite horizon, we are arriving to algebraic Riccati equation. So now, Bellman optimality, some of the extension, we can go ahead with all class of problems for which we can define sub-problems by taking into account the fact that time and spatial complexity and reduced overlapping between sub-problems. We can go to discrete deterministic system in time-varying case, to the continuous deterministic system, finite, infinite time horizon, and discrete stochastic system, and you'll see a few minutes later what are the problems. Now, if we're talking about stochastic system, because this is one of the things we are focusing in the next slides, so dynamic programming in MDPs, the first paper that we found for the Markov decision process was in '57, and it was published by Bellman. And in the case of continuous time stochastic process, there is another paper published in Information Control. It's not the same title. There is an error in copy and paste. It's more or less stochastic processes. So before leaving Aditya to enter into details, just simply saying the reinforcement learning in a very high level, let's say, way to say, it's a class of methods in which agents are taking actions in the dynamic environment. This is exactly what I mentioned at the beginning when we were talking about the environment. For reinforcement learning, the environment is dynamic, and we are optimizing some cumulative rewards. And just for fun, when we are working in optimal control, there are no rewards when we are getting more or less an optimal law, but when we are in computer science, there are always rewards. And dynamical environment is typical Markov decision process. So please.
Thanks, Silvio. In the next 10-12 minutes, I'm going to present a mathematical framework, and this is just to set the stage for the tutorial talks that follow. And the framework is going to be that of Markov decision processes. In general, we can have a situation where an agent is interacting in an environment. In control theory, we would think of this as a controller interacting with a plant. We would follow the standard control terminology that the environment or the plant has a state, which is denoted by xt. It takes an action ut. There are some dynamics, which can be some general nonlinear stochastic dynamics. So the next state is a function of the previous state, action, and independent disturbance. Or it could be modeled as a controlled Markov chain, where the next distribution of the next state is given the current state and control. The system incurs a per-step cost, which is a function of the state and control. And the objective is to find a policy, which in general could be a mapping from the history of observations and controls to the current action. We will think of two types of criteria. The first is a discounted cost criteria, in which the value of a policy is the expected discounted cost of the policy, where the parameter gamma here is a discount factor, which is between 0 and 1, on how much we are discounting the future. And the second is the long-term average. And just for consistency of notation, and the reason for this notation would also become clear later on, I'm going to denote the average cost case as discount factor equals to 1. Now, the objective is, given a discount factor, we want to identify a policy which maximizes the value function over all, in principle, history-dependent policies. And since the actions can depend on the history of observations and actions, brute force search has exponential complexity over time, and moreover, it's difficult to search and implement an optimal policy. And there are two key results which help us solving this conceptual difficulty. The first is Blackwell's principle of irrelevant information, which says essentially that since we have a Markovian system, there is no loss of optimality in restricting attention to Markov policies. That is, policies which look at the current state to choose their actions. Once we restrict attention to Markovian policies, for the infinite horizon case, if we look at time homogeneous policies, that is, policies which are same over time, we can write a fixed point equation to evaluate the value function of a policy. Now, there is a similar fixed point equation for average cost. I'll come to that in a bit. And the key implication of Blackwell's principle of optimality is that if at each step in this equation we choose the action which minimizes the right-hand side, we will identify an optimal policy. The first equation is known as the policy evaluation dynamic program, and the second is known as optimality dynamic program. Now, these are just fixed point equations, so we need to understand whether there is a solution, how do we find a solution, and so on. And a key concept to understand this idea is the idea of Bellman operators. So for a given policy, the Bellman operator is an operator on the space of functions on the state space, which is defined as really the right-hand side of the policy evaluation dynamic program. And the advantage of defining this Bellman operator is that we can write the dynamic program as a fixed point of this operator. We can define something similar for the optimality Bellman operator. And in addition to the optimality Bellman operator, we would define something which is called the greedy operator with respect to a value function, which is simply looking at the policy which gives the argmin at the right-hand side. This, in general, could be a set-valued function because there are multiple argmins. And again, with the optimality Bellman equation, we can write dynamic programming as a fixed point of the optimality Bellman equation with the additional result that a policy is optimal if and only if it is greedy with respect to the solution of this fixed point. Now, given this, we can look at properties of Bellman operators. The key property is that of contraction. Given two value functions, if we look at the distance between the Bellman operator applied to these two functions, the distance is less than equal to the discount factor times the distance between the value functions. And the choice of distance here is the supremum norm. And the other important property is that of monotonicity. If one value function is less than the other, then Bellman operator applied on them would be less than the Bellman operator applied on the other. Monotonicity can be refined because in the sense that if we know that one function is less than a certain amount, then when we apply Bellman functions, that amount gets scaled by gamma. And the implication of these properties is, since we have, at least for discount factor strictly less than 1, contraction, we can argue about existence of solutions using ideas from Banach fixed point theorem. And since we have Banach fixed point theorem, we can use standard ideas of Picard iteration and so on to compute the solution of the fixed point, which leads to standard algorithms to compute the solutions. The average cost setting is a bit tricky. There are various ways to look at it. In the interest of time, I'm not going to go into details, but simply mention two high-level ideas. One is that the basic intuition is as the discount factor goes to 1, the average cost is related to discounted cost, and the precise relation is 1 minus discount factor multiplied by discounted cost converges to the average cost. This is due to a result known as Tauberian theorems in analysis, which says that the able limit of a sequence is equal to its Cesaro limit. So we can look at what happens to Bellman operators with discount factor equal to 1. The key challenge is we no longer have a contraction. We only have a non-expansion in the supremum norm. But instead of the usual supremum norm, if we use another norm, we can still apply fixed point theory. And the idea is to think in terms of the ergodicity of the Markov chain and look in terms of the span semi-norm, which is the maximum of a function minus the minimum. And in general, we have contraction in the span semi-norm, which continues to hold even when discount factor is equal to 1. So we can write down we can say that the Bellman equation has a solution when discount factor is equal to 1, and that equation says that the span of Bellman update minus the value function should be 0, which gives the standard average cost optimality equation. Similar idea holds for the optimality case. Just as a specific example, if we go to the linear quadratic example that was presented earlier, look at the precise definition of the Bellman operator, do a bit of algebra in terms of completion of squares and finding the minimum, we find that the solution is the usual Riccati equation. Now I'm going to briefly talk about some of the solution algorithms. And the basic algorithm relies on the fact that the Bellman operator is a contraction, and this is value iteration. The idea is we start with an initial guess of the value function v0, keep on applying the Bellman operator over time. On the side, we keep on computing what the greedy policy is with respect to that Bellman operator, and we stop when the distance between the next Bellman operator and the current one is less than certain epsilon, and this gives us certain convergence guarantees, and the same idea works for average cost, except that we have to renormalize things at each step. The second algorithm is that of policy iteration, where we are taking a policy, evaluating what is the performance of that policy, and then taking a greedy policy with respect to that performance and continuing this step. Policy iteration gives us monotonic improvement, and if we are in finite state and action spaces, that implies we would converge in fixed time. And it continues to work in the average cost case. The next idea is that of linear programming. Due to monotonicity, we have a characterization of the optimal value function as being the largest value function which satisfies the given optimality equation. And we can write this in terms of a dynamic program, both for discounted and average cost. And we can take the dual of this dynamic program, which gives us a primal and dual characterization of the optimal policy. These are only exact methods. In practice, we would have to go beyond exact methods, look at different approximations, common one being model approximation. So think of if we are solving a continuous state model, we may do state aggregation. We may have approximate dynamic programming, where we do not compute the solution to the Bellman operators exactly, but with some approximation. We can have function approximation, where we are approximating everything on a linear subspace. Or we may have sampling-based methods, where instead of taking expectations, we choose compute approximate expectations via sampling. Now, very briefly talking about the general idea for learning. So the setup is same as that what we talked about, except that the system dynamics and per step costs are not exactly known. There are two types of problems. One of offline learning, where we might either have an approximator, so a system simulator, or access to offline data, and we want to compute an optimal policy based on that. Or online learning, where we are interacting with the environment and learning things as we go along. The key question to ask is that of asymptotic optimality. The policy that we are learning with time, this is going to be something which is stochastic because it's a random process. Does it converge to the optimal policy as time goes to infinity? This is the leaf that we want from a good learning algorithm. And there are various algorithms, including model-free and model-based algorithms on that. Next question is that of sample complexity. How many samples do we need to find a good policy? And that of regret, how well we are doing if we compare to what we could have done had we known the optimal policy upfront. There are various challenges. In the interest of time, I'll just elaborate on one, which is the most important one, which is exploration versus exploitation. That is, if we know something about the system, should we choose an action which exploits it, or should we try to learn more of the environment? This is related to the old idea of dual aspect of control as well. Uh, in general, about learning algorithms, the high-level idea is that given any algorithm that we have for solving MDPs, we can design a sampling-based algorithm for that. The most commonly is a Q-learning algorithm, which is a sampling-based algorithm for value iteration. And we have similar approximation algorithms for other things as well. The other common idea is model-based algorithms, in which, given the parameters of the model, we can have different ways in which we tackle the exploration exploitation idea, the first being certainty equivalence, in which we assume that the estimated parameters of the model is the true parameter and use a control corresponding to that. But we add some noise in while applying our control. Second is related to upper confidence bounds, in which instead of using the estimator, we use something which is an upper confidence bound of the true value, or using a Bayesian approach where we sample from the posterior, and these all give different ways of trading off exploration versus exploitation. Now, one thing that we had talked about was linear programming approaches. One can ask, what do we do with linear programming when there are continuous state spaces? We get linear programs which are in infinite dimensions, and there are ways in which one can use data-based algorithms to solve that. The talk by John Legros is going to talk about linear programming-based approaches to solve data-driven control. Then we can ask, what do we do beyond asymptotic optimality? And the first thing is sample complexity. The idea of sample complexity is given a approximation level epsilon and a probability p, how many samples are needed to find an algorithm which, with high probability, converges to something whose performance is within epsilon of the optimal performance. And usually the way this goes is one would pick an algorithm, try to characterize what is the sample complexity of that algorithm. These are known as upper bounds. And the other is trying to identify lower bounds, which is trying to say that are there models which no algorithm can learn without using certain number of samples. And typically these bounds scale with the size of the state and action spaces and have certain scaling with respect to the number of parameters, the accuracy level that we want, and the discount factor. Now, the talk by Kai-King Zhang is going to talk about establishing sample complexity upper bounds for a specific class of algorithms. The next idea is that of regret. And in regret, one asks, what is the performance of my algorithm? And how does this compare had I known the true system parameters upfront? And again, for regret, you could take your favorite algorithm and try to establish what is the upper bound on regret for that algorithm, or try to establish lower bounds, which is given any algorithm, given up certain models, there are no algorithms which can do better than that specific thing. And again, in this case, the upper and lower bounds match. A key question is, how do we establish lower bounds? And the talk by Henrik Sandberg and Ingvar Zeman is going to talk about methods using which we can establish lower bounds by using ideas from information theory. And finally, I'll briefly talk about things which are not covered. One thing is beyond cost minimization. So far we have talked about only minimizing the expected cost. We can look at other types of things like constraint MDPs if we have constraints. Special class of constraints are when we have safety guarantees that we want that the system state should not enter into a particular state. We can look at risk measures that we do not want the tail probability to be beyond certain quantities, or we can look at distributional robustness, which is cases in which we do not know the model precisely, but we want to be robust with respect to the uncertainty in the model. And there are other learning frameworks as well. For each of these things, we have different types of learning frameworks. So beyond cost minimization, there are computational aspects for this, which I haven't touched about. And the real world is not a Markov decision process. So we have partial observability, multiple agents, and so on. There are situations in which we may not have access to a cost function. For example, if we are thinking of self-driving cars, there is no cost function which gives what a good behavior is. And in recent years, there has been increasing interest in learning for pairwise comparisons, which is happening in reinforcement learning with human feedback. And the last talk by Mariam Kamkapur is going to talk about inverse RL for constraint MDPs, which is going to connect all of this. And I must also congratulate Mariam on getting the ECC award for that. And with that, I would stop. Thank you. And the next talk is by Ingvar.
Okay. All right. Hello, everyone. It's fun to be here. I was a PhD student with Henrik, and I'll be talking about work we actually did together during my PhD. And also thanks Silvio and Aditya for the invite and for the nice introduction to all this material. So I'll be talking about information theoretic lower bounds, or fundamental limits to learning to control, which will mostly be based on the article at the bottom of the screen. And before I begin, I'd like to sort of address the question of, I mean, at a high level, why do we study fundamental limits? Why do we care about these things? You might have tried to train an RL agent at some point, say Mujoko or something. You know, this is your ambition. Your ambition is high. Unfortunately, so is your training loss, and what ends up happening is something like this. And of course, you know, you might say, Ingvar, okay, come on, this is just in sim, but I mean, there are certainly examples that, okay, so this was a video that was supposed to play, but I have a PDF now and not Keynote, sorry about that. It's an Uber running a red light. So there are certainly examples, not in sim, where things go wrong using learning-based control. And I think that the controls community is sort of very well positioned to analyze these things. I mean, we have a long-standing history of studying fundamental limits. Okay, so with that being said, what I want to talk about now is the sort of adaptive LQG problem, or in the sort of framework that Aditya put it, it's sort of the online learning problem. The dynamics are just your standard sort of state space model, let's say. This is a Markov decision process, it's a state space model, it's both. You can also look at the partially observed setting. In that case, it would be not just a Markov decision process, but a partially observed Markov decision process. But we can mostly focus on the sort of case where the state xt is observed. Okay? And the noise I'll just assume to be IID mean zero Gaussian. So the sort of crux of this problem is that the parameters a priori are not known to the controller or learner or the sort of learning system, if you will. So the problem is to regulate the system all the while estimating the parameters, or at least estimating the information necessary to make good decisions for the control cost. So basically, choose a policy that only depends on, you know, your observations, not on the parameters, because you don't know this. Using a single stream of data, so at every time point I need to make a decision, and I can only use what I've seen so far. And my goal is to minimize this criterion, which is just the sort of LQR cost. Okay, and we'll be assuming that everything is nice and regular, so stabilizability, detectability, all these things. And just because the parameter is unknown, I won't be able to sort of attain this optimal cost. So V star, I'll denote the optimal cost. I mean, consider the situation where there might be two different parameters, I don't know which. If I do the optimal policy for the one, it's not going to be optimal for the other, basically. So there's some, you know, estimation involved here. And the measure you typically sort of define to address this is the regret of a policy under a certain model, which I'll just denote by R. Okay? So if the generative model is theta, and I play policy pi, I incur regret RT, which is 0 if and only if I play the sort of correct policy, which is the, say, the composition of the solution to the Riccati equation with the Kalman filter. So what I want to talk about today is how to prove lower bounds for this problem. And more generally, perhaps like how to give you ideas how to prove lower bounds for learning-based control problems. I mean, this is kind of the hardest problem in some sense, the online problem. So more generally, to give you ideas what methods you might use for, proving lower bounds, performance lower bounds, or fundamental limits for learning-based control. So the crux here is that this quantity f should sort of depend on system properties. I don't just want it to be some dimension factor. I want it to be something that tells me that if I have poor controllability, this task is going to be hard, or something like this. And I'll get back to that later. Yeah, so stability, observability, sort of dimensional quantities should be captured by this f. And I'll also get back to why the square t factor and not, say, log t appears here. Yeah, and so you might also notice this sort of soup appearing. And that is, again, related to the fact that, I mean, if I was only looking at this inf over one parameter, then I would always just play the sort of optimal policy for that parameter. So I better somehow model some uncertainty. So the way I do it here is I look at a small ball around the true parameter, and I just say that some adversary has some strength to choose the generative model, so the model generating the dynamics, which has sort of some epsilon radius to confuse me, let's say. And I better perform well, at least on this epsilon radius of possible generative models. So in information theory or statistics, these would usually be called local minimax lower bounds. And the way I want to think about this is a regret lower bound here is a fundamental limit to adaptive control performance. So before I proceed and tell you how to prove things, or at least give you an idea, I would sort of like to introduce what I'd call a sort of reasonable strategy for this problem, which is certainty equivalence, as Aditya and Silvio mentioned. So suppose you have this unknown plant. So what is a reasonable strategy for adjusting your gains here? And let's just assume that it's fully observed. So the C matrix is the identity matrix, and there's no output noise. Certainty equivalence is just you estimate your state parameters, so your A hat and your B hat. So these are estimates of A and B, your tuple. So I mean, you have access to this data, the x's and the u's. So you can certainly form these estimates by linear regression, say. How do you get the gain? Well, you sort of do the obvious thing. You just plug them into the Riccati equation and hope for the best. Okay? And if you do this, it turns out that you end up with junk. But if you add a little bit of noise, you'll get a little bit of more exploration. So this is related to the exploration-exploitation trade-off. If you do scale this noise correctly, you can prove that you get sort of optimal-ish regret. There's still some stuff to be settled here, but more or less optimal. And there are similar ideas that can be used to sort of the partially observed settings. But I won't go into the details. I'd rather talk about the sort of lower bounds, not give you an exact overview of everything that's been done. Speaking of overviews, sort of there has been quite a bit of work, and sort of the state of the art is more or less that you get the dimensional dependence has been settled, but the sort of dependence on system quantities such as controllability, observability, stabilizability as such has not really been settled. And you'll notice that there's a gap between the sort of instance dependent, which is fix an instance, what's my regret going to be, and the worst case, an adversary chooses the environment, basically. And it's exponential in the worst case, whereas in the dimension, whereas it's not in the sort of average case, let's say. Okay. Now, how would you go about analyzing, I mean, online learning in LQR or the adaptive control problem? How would you prove a lower bound for this? So the first thing you do is probably just write down the thing you're trying to lower bound, which is the following thing. And what you can do is you can observe that basically because there's a quadratic form proof for LQR optimality, and it turns out that LQR has this very nice quadratic form for the regret. So what you'll observe here is that, so the parameter that's unknown, that's theta, right? And what you'll observe here is that your inputs u's are sort of like an estimator of theta of, so the controller k of theta in the direction xt. And that's very much the idea. Before doing that, we'll also note that we can always relax this soup to an average. So now we basically have a Bayesian estimation problem. So we've relaxed this sort of local minimax problem to a Bayesian estimation problem. And that's typically what you do in proving local minimax lower bounds. Okay. So I now have a prior distribution over parameters. I have a decision rule which outputs inputs. And I'm telling you I'm going to view my control inputs as sort of estimators of the optimal policy. So I'm more or less in a setting of statistical decision theory at this point. Or I can view it. I've reduced it to that. And that's exactly what I'm going to do. I'm going to lower bound these quadratic estimation errors using ideas from estimation theory or information theory. OK? And again, let me just reiterate that this soup is necessary because otherwise the inf in the last slide would just, everything would be 0, basically. Yes. All right. So because everything is nice and quadratic, the sort of obvious thing to do is to use Kromer-Rao, or the Bayesian version of it, because I just told you I reduced it to a Bayesian estimation problem. Ignore the bottom right. That's not supposed to appear yet. Sorry about that. That was supposed to be the punchline. Right. So I want to estimate this k of theta quantity. What I can do is I can basically just apply Venturi's inequality as is, and I'll get a lower bound of the following form, which tells me that, you know, the more information I get, the less the estimation errors. And the information in this case is sort of the Fisher information matrix, which for LQR takes the following form. So it's this quantity in the middle of the screen, which is just sort of your, you can think of it as the sort of excitation energy of your covariates, if you will, and then summed over time. And if you sort of apply this observation to the sort of form, the form of the regret on the last screen, what you end up getting, there are details here, but you know, morally speaking, you can lower bound the regret by t times 1 over the smallest eigenvalue of this Fisher information matrix. Morally speaking. There are obviously details here. And let me also mention that this sort of, for those of you who haven't seen the Fisher information matrix before, in the bottom left of the screen, I wrote down the least squares estimator for estimating A and B. Basically, what this says is that if the Fisher information is small, your least squares estimator is ill-conditioned. So it's something like capturing the hardness of how easy or hard it is to estimate something. Okay? So, okay, punchline from this screen is that regret is lower bounded by t, so I have t rounds, and the Fisher information matrix over those rounds. What does that tell me about regret? So, to talk about that, I need to introduce one more idea, and that's the fact that, you know, I can't just lower bound something by t. I mean, that's not true, because I don't know how big this Fisher information matrix is. It might, in the worst case, it might scale like t, so then I would have t divided by t, and I get a lower bound that's like 1, which is not very good. So there's one thing I haven't mentioned. That's this like exploration-exploitation trade-off that Aditya and Sylvia were talking about. So let's run a little thought experiment and think about what happens if we play the optimal policy. Okay? So for this policy, it turns out that the Fisher information matrix takes the following form. How much time do I have left? 5 minutes? OK, cool. Thank you. And what you'll notice with this form on the rightmost is that it's basically the outer product of two tall matrices. So identity kx, ignore the xt. That's just some covariance matrix. And then outer producted with identity k star, right? So that's always singular, because it's an outer product of tall matrices. So in particular, this information matrix, whenever you play a feedback controller, is always a singular matrix. So its smallest eigenvalue is 0. So that's an identifiability issue right there. Okay, so I told you this is the case for the optimal policy, but what if I run an arbitrary policy? What happens then? Well, so you can prove that the smallest eigenvalue of the Fisher information matrix, actually you can prove more than this, but this is sort of the moral of it, is upper bounded by the regret of your algorithm. So whenever you have small regret, you also have bad exploration to some extent. So this very much captures the exploitation-expiration trade-off in LQR. So LQR has issues with closed-loop identifiability. And the exploration-exploitation trade-off is non-trivial. So this kind of gives us the proof sketch, actually. So in the last slide, I had that the regret was lower bounded by t times the inverse of the information matrix. But now I've also upper bounded this information matrix by the regret. And sort of just doing the critical balance here, I end up with regret that scales like order t. And I haven't really told you about the constants here, but we do get quite reasonable constants using this proof approach. That is sort of the result I'll talk about now. Real quick. Okay, so again, we'll just assume that we don't know the parameters A and B. So this is the state feedback setting. Y is known to be the identity. So C is known to be the identity, and there's no output noise. You can prove the following thing, that this sort of local minimax regret scales as follows, where P is the solution to the Riccati equation. So in particular, if the closed loop is close to marginal stability, the right-hand side will diverge. So it kind of captures that hard to control implies hard to learn to control. Let me just illustrate this really quickly. So for a scalar system, suppose control authority is lost. So control authority here, because it's scalar, is just captured by the parameter b. So as b goes to 0, you lose control authority, and the lower bound here goes to 0. It goes to infinity, whereas the lower bound of previous work, that's kind of why I had that orange line in there, was going to 0 as control authority was lost, which was sort of the opposite behavior that you'd expect. But again, so if they're hard to, if problems are hard to control, they tend to be hard to learn to control as well. That's sort of the punchline. Okay. I think I have a little more time. Yeah. So another sort of corollary we can extract from this is a curse of dimensionality result. So if I look at a particular system, so something that's very integrator-like, which is, takes a long time for me from the first mode to reach the last mode to control it, so it's hard to control it in some sense. We can show that this exhibits exponential complexity in the state dimension in terms of the regret. And more generally, this depends on the controllability index of the system. I also have results for the partially observed setting. There are no big surprises here other than that observability takes the role of controllability. I'll skip this slide for the interest of time. But sort of as a takeaway, I think abstracting beyond, okay, we can prove these results, which are interesting in their own right, but sort of the message, I think, is that if I have a learning problem, which is a learning for control problem, let's say, I mean, control problems are very much decision problems, and you can often maybe not cast them, but reduce them to statistical decision problems. And in statistical decision theory, there is like a well-established kind of literature that allows you to prove fundamental limits, and it's just a matter of like meshing these things together to some extent. And what we did here was apply this to stochastic adaptive control, and kind of this allowed us to characterize the exploration-exploitation trade-off in LQR and LQG through sort of this characterization of the regret bounding the Fisher information. Yeah, and if you in LQR, it turns out that this is sort of the optimal scaling of the regret. Okay, so these are references. If you're interested in further reading, send me an email. I think this might be too small to see, but yeah, send me an email if you want the slides. Thanks.
Let's see, Ingvar, if you have one question in order to fit with the time. Somebody there. 1 second. Thanks.
Thanks.
There are two questions, one on the right and one on the left.
Sorry.
Okay, sorry.
Okay.
Hi, nice talk. I was wondering about the small ball epsilon. There seemed to be that ball, and then at the end you made a choice. You made it depending on time, or it just disappeared. I mean, what happened?
Yeah, so I mean, okay, this is sort of a proof detail, but there's a radius of epsilon that needs to be small enough in terms of the, well, small enough and big enough at the same time in terms of the time horizon. It will shrink to 0, like as the time horizon goes to infinity, basically. So it's an arbitrarily small ball in some extent, but it does have a certain scaling.
Right, and that is the only reason why you get the dependence on time, or you would get it anyway?
I mean, so think of it this way. Let me take a step back. So suppose I'm trying to solve this min-max problem where I'm minning over controllers and maxing over parameters, right? If there was no max here, the min would just be the optimal policy. That would be the argmin, and that would give you 0 regret. So somehow we need to model the fact that there is confusion about what is the true parameter, right? I mean, I could have actually picked a constant radius over this soup, but the best I can do is to let this go to 0 at this like rate t to the minus 1/4, I think it was. Okay, thanks.
Thank you.
Okay, great. Thank you very much for the introduction, and thank you very much for the invitation and organization. So it's really my great pleasure, and it's also my honor to be here to talk about something I feel very excited about. So today I'm going to talk about understanding, or try to understand, cost-driven state representation learning for control. So I will be talking about that. You know what do we mean by that in a second. So before I forget, this is a joint work with my amazing collaborators, Ras, and Surit. And also, we want to express special thanks to Alex and Horia. So a little bit background about the problem. So basically, I got very fascinated by robot learning during my postdoc stage. So I was always like asked the question from many like robot learning people. So so there are a lot of very fascinating examples here. So the first one is a well-known one, which was done by OpenAI. It's actually used as one of the most prominent examples of the success stories of reinforcement learning or deep reinforcement learning, which is learning dexterity of robot arms. There are also some very, I would say this is definitely not a complete list, but there are some successful stories of using deep reinforcement learning for robot locomotion and for robotic manipulation. So what fascinated me at that time was like, as a control theorist, when I entered this area, it's really like there are a lot of things going on there. So can we try to put on our control theorist's head and try to understand some ideas and some principles behind them a little bit more? What I was asked a lot during that time was like people asking, what's the right state? So many control and reinforcement learning problems, as Aditya mentioned in the introductory lecture, are based on this state space model. Okay? In a simple example, like the textbook example of mass spring damper, we know the position of this mass corresponds to the state. And then we can formulate the state dynamics and try to analyze this system. But in practice, when this robot learning people, they try to solve some a robotic manipulation problem, for example, usually the input of the system is very high-dimensional. So they take this like cutting the onion example, like if you want to cut an onion with only visual input to the robot, what's the right state? So I wasn't able to provide a very good answer to them. So they were asking, should I memorize every single piece of the onions or some like other transformation of that? In other words, we were interested in the question that what is a good state or what is a good state space in these practical problems? And more importantly, how to learn it from data. Okay? In fact, this is what in the deep RL literature, they refer it to as latent model learning for control. So there are a number of empirical works that have attempted to solve this problem by learning a latent model. So in solving problems like control robotics in simulators, or like playing Atari games, or playing Go games, especially in the case where the state space can be very large. So to make sure we are on the same page, by talking about this latent model learning, I'm mostly talking about the following pipeline. You take a bunch of data, which is usually the streaming like video or image data of high dimensional as input, And then when we say latent model learning, you are basically trying to learn this green part, okay, so that you can do planning on this green part by taking this input and translate that into some latent state. And then you do planning there to try to find a good policy. We call it latent policy. And that's the language they use in this empirical world. This interface, actually, with the environment, there are 3 quantities that's very essential. And I will mention that later with more details. But the 3 quantities, as we know, are the observations from the environment, and actions you have taken, and the cost you have received. So a little bit more details. So setup we consider in this case is controlling a partial observable system. So basically, you consider a sequential decision-making problem with time index t, starting from time 0. And then at each step, agent will observe some observation yt. And then it will take some action based on the controller, based on the history he has received in general. Okay? This is a very familiar setup for us. And then it will receive some cost. And then we consider, in this case, a finite horizon case. And if this underlying state evolves in a Markovian way, this goes back to the partially observable Markov decision process. And there are a lot of applications of this model. So if you really want to formalize what this deep RL people are talking about, let's try to decompose what they are really doing. Usually what they are doing in this latent model learning process is that they want to learn a representation function, okay, in general, which maps the history or the information you have until time t into a latent state, zt. In our language, that's a filter, in fact. And then based on this latent state, and you construct latent dynamics, and then you try to solve for the policy in this latent space. And then this overall policy is going to be a composition of this representation function or compression function of the history and the policy. In the setting, usually they consider is that you have to learn this representation function and the policy together from data. So this is a setup. But really, the motivation of this specific work is that there are a lot of work trying to address this problem. There are several very high-profile ones. So one example is this called value prediction network. And also, people are trying to use self-supervised learning or self-supervised prediction methods to try to find this latent space or latent state space. And also, a very high-profile one is people talk a lot about this in the deep RL world. It's called word models. It was actually argued by people to be a path towards autonomous machine intelligence. And also, there are some other examples I wouldn't have time to talk more with more details. Like mu0 is another famous example. And also, like for robot learning people, this Dreamer series of work is also a very celebrated work. So despite this exciting empirical advances, theoretical understanding of this method is relatively lacking. So what latent state spaces are these empirical methods essentially learning, especially with a finite number of samples? And this is unclear at that time, even for very basic partial observable control systems. So if you really think about this problem, it's a POM-DP or it's a partially observable control system. If these methods are really good, they should at least pass the sanity check for very basic control setup. Also, from this very basic control setting, we can gain more insights into these empirical methods. So the high-level question we asked was, what's the minimum condition or the right objective for latent model learning that works for downstream control tasks? Remember, we mentioned 3 quantities when you interact with the environment in this setup. In the interactive decision-making setup, you have observations, you have actions, you have cost. So we read a lot of empirical papers. We're trying to characterize its literature into the following 3 types of works. So the first one is based on observation. They call it observation-driven. So one famous example is called reconstructing the observations. So that's what exactly this word model is trying to do. So basically, I use the first figure from that paper. Basically, you take this image as input. You want to use some neural network, let's say autoencoder, and trying to basically reconstruct this specific image. And then you just take out the like the latent state as a state. Another type of method people use a lot in this deep RL world is called action-driven method. What they are trying to do is that they want to try to find a good latent space such that you can predict the action very well. In other words, on the right-hand side, if you start from some state x at time t, and then like there are some action will take you, or a sequence of actions will take you from xt to another state, they use this starting and ending state and try to predict what happened in the middle, or what's the action that take you there. And if what's a good state? A good state should be able to help you predict that thing very well. So that corresponds to the action part. In these two types of methods, usually what these people call these methods are task agnostic. Because when you are doing that, it has nothing to do with a control task on the downstream control task, has nothing to do with the reward or the cost function of this task. So it is good because it can be universal. Usually, in this, especially if you use some neural network there, they can learn kind of universal features that can work in a bunch of tasks. It's what we mean by multitask or generalizable. However, there are also some cons corresponding to this type of method. For example, if you just reconstruct the image, okay, as we can imagine, it may contain some control irrelevant information for the task. Because of that, you can easily get distracted by some noises in the images. And also, this observation can be very high dimensional if you really want to reconstruct it very well. So there are also some computation hardness or computation challenge in this setting. So the last type of method that's related to the third quantity I mentioned is called cost-driven method. So this is what a method used in this value prediction network, or mu0. So what they are trying to do is that I want to find, so x here, there's a mix of notation because I used the original figure from that paper. So x is right now the input. Okay, you want to compress x to some latent space s by finding this f encoder. And what's a good encoder? A good encoder should be able to predict the value function or the reward function very well, because they argue that reward function is a more direct. It's a more direct quantity. It's task specific. It's something you are going to use for planning, for optimal control learning later. That's why they call this more direct. The other question was, can this cost-driven direct latent model learning approach truly solve partial observable control problem? So the simplest setting we can think of is linear quadratic Gaussian control problem as control people. So this is something we are very familiar with. I guess I don't have to spend more time on that. So we consider a finite horizon, a linear time varying LQG problem with linear dynamics, Gaussian noise, and partial observations. Okay, and the cost is of quadratic form, and the terminal cost is also very quadratic form. And the goal is to try to find the optimal policy to minimize this accumulated quadratic cost. So if the model is known, we all know that you can do separation principle. You can try to find the optimal policy by first do a filter, the Kalman filter, and you find the estimate of the state z, and then you try to solve this problem as if it's a fully observable one. If you look at this equation, if you really think about this Kalman filter step is essentially a latent space, latent dynamic model in their language. So for an unknown time varying like linear quadratic Gaussian problem, there has been a flurry of recent work that's tried to establish finite sample analysis to learn to control such problems. So the standard treatment nowadays in this type of works is based on learning Markov parameters. So that's based on the system identification approach we are familiar with. So basically, if you unroll the dynamics, you reformulate the problem as a new linear regression problem. In that regression problem, you'll be looking for this Markov parameter. And then you can reconstruct this system matrices ABC from this Markov parameter using, for example, whole Kalman algorithm. And people have, in this literature, they have established how many samples do you need to really identify such a system. So what's the problem? The problem is that this pipeline is, at least in this analysis, in this line of work, that's specific to this linear time invariant system setting. And also, learning this Markov parameter still requires you to reconstruct that y, which can be high-dimensional in this kind of applications. That's why actually they developed those cost-driven or direct latent model learning methods. Our approach is try to instantiate what they are doing there into our linear quadratic control setting. In that case, if you instantiate, then we can basically instantiate this phi, which is a representation function, as we know that in linear quadratic control setting, it's going to be a linear function of the history you received so far. In other words, what you are looking for here is a linear mapping from history ht to latent space zt. Or you can also write it in a recursive way. That's exactly what Kalman filter is trying to do. And then you're trying to also rewrite this cost as a function of your latent state and also the control action you're using. Then the overall, like the control policy is going to be a composition of this m, which is the representation function, and the control policy in this latent space. Then what this cost-driven method, if you literally do this like translation from their approach, what you're trying to do is that you want to find such a representation function, m, that can help you predict the cost ct very well. That's the objective you are using. You're not predicting like y or concatenation of y. You're trying to predict the reward you receive when you interact with the environment. Okay? So this is a summary of the outline of the algorithm. In the Gaussian case, we know in order to balance the exploration trade-off, you have to inject some noise when you try to identify the system. So similarly, the control input here is going to be just random Gaussian noise. And then the state representation step here is trying to predict the cost. But one caveat here is that we did some modification of this original algorithm, which is actually turns out to be very important, is that we predict some accumulated cost of multiple steps. Okay? This is exactly what people use in mu0, in the sense that that's why they call our value prediction network, is that they're predicting the value function, not just the reward function. And like I mentioned, this main modification of the previous cost is that we are now predicting the accumulated cost. And the main difference from the world model paper originally was that they are doing this representation learning step by reconstruction-based method. There's nothing to do. They had nothing to do with the underlying task or the reward function, but just by reconstructing the observation y. But we replace that by this cost-driven method. So this kind of contrasts this method and the traditional SysID method we talk a lot about in the literature. So in the cost-driven method, you are trying to map this h to some latent space z, such that you can predict that accumulated cost very well. And then you use that to generate a sequence of underlying states, which we call zt. And then you use this sequence to reconstruct a latent space model. But in the classical SysID, at least in this subspace method or the Markov parameter-based method I mentioned, they do the following thing on the bottom. Then what do we have for this kind of method? So can this method really solve LQG? So the answer is that, in fact, yes. So under assumptions including like the stability of the original system, the controllability, the L-step controllability means that after L steps, the Gramian would be like full rank. And also the observability condition of the cost, you can show that a state representation function can be learned with high probability. And also based on that, you can learn a good latent policy that can, as the number of samples grows, you can achieve the near optimal policy by using that. A small caveat here is that there's a separation between the first L step, which is the time that the system become, like the controllability Gramian become full rank. There is a separation between the sample complexity there and the sample complexity after that. So I'll be talking about quickly in this one-page slide. So basically, the key message I want to summarize here is that for LQG control, cumulative scalar cost is informative to recover the near optimal state representation function. And the insight of predicting cumulative cost, not just cost, but cumulative cost in latent model learning has also been empirically observed in mu0. There are several technical challenges we have to address in order to obtain the results in the previous slides. The first one is that if you really look at this problem, because the cost is of quadratic form, essentially, if you want to predict cost, that will give you a matrix like quadratic regression problem. Okay? The covariance of this regression problem is going to be a product of Gaussian. It's a non-classical setting compared to linear regression. And also, in the first L steps, the latent states are not fully excited. There are also some challenges you have to address when we try to do sysid there, because the covariance there will have covariance that's rank deficient. In other words, the system is not fully excited in the first L steps. That actually corresponds to the worsen of that sample complexity in the first L steps. Because of that, the latent model will only be identified partially, but then actually you can show that that's enough for you to get a near optimal controller in this case. Lastly, is that because of this rank deficiency issue, you have to do this matrix factorization more carefully, and that's the last bullet in this slide. How many times? Sorry, OK. So I guess I will just summarize. So there are also several highlights I want to mention because it's a tutorial session, but I guess we can talk about that offline. To summarize, so basically, so what is a good state space for practical control and RL tasks, and what's the objective to learn it? So that's a question you ask. So the state representation of LQG can be learned by predicting cumulative cost. And we provide some insights into this empirical method. And in general, I believe there are many open questions state representation, bridge ideas and insights from both control and learning. And that concludes the talk. Thank you.
Thank you also for the invitation to be here. I'll make sure to skip half my slides so Mariam gets a few minutes in the end as well. OK, quick word of thanks to my partners in crime on this, Andrea, Lucia, and Matilde, my most recent ones, and a list of others I've worked on results I'll talk about today, and our sponsors, the National Center of Competence of Research in Automation and the European Research Council. If you want to know more about the NCCR, there's a lunchtime session tomorrow. Drop by, and then it's about research in general. It will be represented there. OK, I will skip through most of this because Silvio and Aditya already mentioned in the beginning. It will be a talk about dynamic programming and the characterization of value functions. The standard way to do it, the most usual way to do it, is as fixed points of operators, which is very nice, but if your space is of high cardinality or has infinite components, you cannot really use that characterization directly. Then people do approximate dynamic programming. You see the classical references there, where you use neural networks or linear subspace of features to parameterize your value functions and solve the problem there. A different approach, which was also mentioned in the introductory talk, is using linear programming. Then you forget these equalities and you go for the equality constraints or the fixed points. You go for a linear program. Also very nice, theoretically very elegant, and very strong mathematical results behind it. If you want to know more about this, the books by Hernandez, Lerman, and Lazer are sort of a good place to start. But it's also very difficult a problem to solve afterwards, because you get, if you have continuous components, an infinite-dimensional linear program, which you cannot solve directly. There's the SDPs that Lazer has been working on. If you know the dynamics, it's not really a data-driven construction. But then you have to, you do the moment hierarchy. You have to solve very big SDPs, which is also a pain sometimes. What I'll talk about today is how to bypass this and get a solution, try to get a solution more cheaply. So I will be, again, doing a restriction to the value function space subspace spanned by features. And I will talk about the robust program that arises when you do that, right? So you get a finite dimension, finite number of decision variables, you have an infinite number of constraints, you got a robust program. This will be completely data-based. It allows you to make completely data-based. I'll say a few words about this. It allows you to incorporate your data in a batch way instead of sequentially. Has some advantages, but also disadvantages. But you have a standard linear program, not an SDP anymore. It's an easier class of problems to solve. The but is also one of the drawbacks because it doesn't allow you to, you have to keep all your data with you. If you want to do it in large data context, you get a very big linear program. You may not be able to solve this. You need to find ways of actually storing the data. You get guarantees, theoretical guarantees, but I'll say in a minute that there's caveats to that. It's correct mathematics, but practically sometimes there's drawbacks, even though the math says this would work like a charm. Yeah, and then I'll give you an introduction to how to do this. So, quick introduction to the optimal control using linear programs. Start with a stochastic stochastic discrete time system. I use psi as the noise, x and u are the state and actions, and x plus is just the next state. And then I have a stage cost function. And we've seen several times this type of equation. This is the value that's associated with a policy. You have a policy that tells you which action to take at which state. And the value of that is a discounted cost. Like here is an infinite sum, an expected infinite sum of the stage cost, the L computed at x, and the policy that you played. Okay? What you want to do is to find among all of the policies that you can take, all of the functions that map x into u, your states into your actions, you want to find the optimal one, the one that attains the minimum in this sense, in this cost. Okay? The characterization is through the Bellman equation. We saw that again in the beginning. If you have a fixed policy, the pink box on your left is the value associated with a fixed policy. That's a linear equation. If you're in the finite state and action setting, you can just solve it like a linear equation and get the value associated with the policy. That's called policy evaluation. Or you go directly for the optimal policy. That's the fixed point equation on the right, which has an infimum over all the inputs on top. And that makes this operator, this tau t operator, a nonlinear one. So you have a nonlinear set of equations to solve, which is a bit more challenging. And all the dynamic programming methods rely on the fact that these operators are monotone and contractive. So you can do value iteration or policy iteration, or the linear programming, the one on the right that I will be talking about today. So all of these methods rely on these basically two properties. Okay, on the linear programming, also Aditya mentioned this earlier. This is, what you can do is take your Bellman equation on the blue box, or whatever color that is on the right, and then relax the Bellman constraint from an equality to an inequality. And then try to use a cost to push against this constraint. So the constraint, this is an optimization problem. I'm trying among all functions in the function space, I'm trying to find the one that maximizes this cost. This is sort of an expected value cost with respect to some measure C. The C is a choice I'm making, a non-negative measure C. And then the bottom is basically the Bellman equality relaxed to an inequality. Okay? And this has to hold for all states X. Okay? Now you can prove that whatever cost you choose, whatever measure you choose for C, you will retrieve the optimal value function by solving this linear program. More or less, you will retrieve the optimal value function wherever C is supported, so except a set of measures 0 in C. But if your measure C is supported everywhere, then you just get it pretty much everywhere. You can obtain this. This is a nonlinear program to start with because T is a nonlinear operator, but you can do a further step and just parameterize by all x and all u. You get the blue box on the bottom, which basically is a linear constraint in the space of functions. It involves the dynamics, so the function is computed at dynamics, which dynamics could be as nonlinear as they want. But as an operator, this is a linear operator, the one in the blue box. So that's a linear constraint. So that's a linear program on, albeit an infinite dimensional space with an infinite number of constraints if you have continuous quantities. You have to keep me on time, so you may want to give me a warning every now and then. I don't see any. Ah, there's one. Okay, which is not working. Great. Okay, just wake me up. If you find this optimal value function, you can extract the optimal policy. But to do that, you have to know the dynamics. You have to perform this minimization that's shown on the slide. And if you don't have the dynamics, if you're in a data-driven context, you can't really do it. But the way around this is just use Q functions. Q functions are basically the same as value functions, where value function is what you get if you play optimally. This is what you get if you play whatever you want for your first step and optimally from then on. So that lets you evaluate your first move with respect to what happens after that. And then if you manage to compute the Q function, it's a fixed point of another nonlinear operator, this F operator that I've written here. If you manage to compute the Q function, then you can extract the optimal policy by simply minimization of the Q function, because the value function is basically the minimum of the Q function over all of the U's. So with a Q function that is parameterized by both state and input, you can actually automatically extract the optimal policy, if you can find it. Turns out that the Q function also admits a linear programming formulation. You have to work a little bit harder than for the value function. This is what you get when you relax the equality constraint for the fixed point equation of the Q function from this slide, and you relax it to an inequality. And then you get, again, something that looks like a linear program. You get a supremum over all Q functions with a measure that maps states and inputs to a non-negative measure on states and inputs, plus a very nonlinear constraint. The constraint has the states cost in it on the right-hand side, and it has an expected value of a maximum, of a minimum over the actions. Because now your action appears twice. It appears in the action that you play at the first step, but also it appears in the action that you play after that. Okay? The problem is now we cannot do the same kind of relaxation that we did before. We cannot parameterize this with all W's because the W is inside the expectation operation. Okay? So you cannot interchange the expectation and the infimum. Like, before we just had an infimum, we had an infimum expectation, you just took the infimum away. Now you have expectation infimum. The infimum is on the inside, you cannot just take it away. One thing you can do, which is what Ben van Rooyen co-workers did a few years back, is to add more decision variables. This is adding basically a value function to the mix. And then when you write it like this is the extra decision variable V. When you write it like this, you're getting a linear program again, but over twice as many decision variables. So you're using the V basically to lower bound the Q, and then you're using the V in the upper bound of the Q as well. So you sandwich the Q between V and the V at the next stage. We also did the same kind of calculation for infinite state systems. You can also get nice bounds if you do this, but practically it's a bit more difficult because you have to solve twice as big a linear program. Another way to do it is to just be lazy and interchange the minimum and the expectation. You shouldn't do that really, because now this is a relaxation. And you shouldn't, in principle, get the right value function by doing this. You do get a linear program because now you can just take, because the infimum is outside the expectation, you can move it away, parameterize over all W, so you have a constraint that's parameterized by state, input, and input. So the input you apply now, the input you apply next. You get a linear program with exactly the same number of decision variables as before, so you didn't make it bigger. Clearly, you get an advantage. The plot on the bottom shows benchmarking on increasing linear systems of increasing dimension. And you see, basically, if you solve the original linear program, your approximation on the left subplot gets worse and worse as the system gets bigger with the same number of constraints, and your computation time gets bigger and bigger. Whereas if you just do the relaxed program, half the decision variables, better approximations, and better time computation. But of course, it shouldn't work because you did a relaxation. It turns out you can show that this relaxed operator is number one, a contraction and monotone. So you can actually solve basically the same thing, find a fixed point. So you can apply contraction mapping and find a fixed point. And it turns out that the fixed point of the relaxed operator is an upper bound of the fixed point of the original Bellman operator. So there is a relation between the two. Moreover, for deterministic system, because there is no expectation, trivially, they are exactly the same. So if you're doing deterministic systems, you don't need to do this doubling of decision variables. And for affine system, in the affine quadratic setting, so if your dynamics are linear, more generally affine, and your costs are quadratic, even if they're stochastic, the optimal policies coincide. So you don't get the same fixed point, you don't get the right Q function, but miraculously, you get the right policy out of it. Which is handy, because you can solve a small problem, get the right policy, and then bypass all the problem. For nonlinear systems, we don't know. That's sort of something we haven't figured out how to crack. You do get pretty much the right policy. The plot on the bottom is a cart-pole system, nonlinear system, where we applied this method. And you see the trajectories. If you do the standard LP and the relaxed LP, you get exactly the same. but we don't have a proof why this should be. Okay. Let me get now to data-driven linear programs. So far, it's been model-based. I'll use the relaxed operator simply because it's the simpler one. So I'll use the relaxed operator from now on. This is a convex optimization problem, which in principle you can solve efficiently. But of course, for continuous state and actions, you really can't, because your decision variables take values in an infinite dimensional space, and you have no way of parameterizing this. Your constraints are infinitely many, because the x and the u are infinitely many. And you also have an expectation to boot, which is also a difficult thing to compute. Okay? So you can't really use it directly. But you can work your way around this. Number one, the standard thing for going from an infinite program to a semi-infinite program is to make the decision variables finite, restrict attention to a subspace spanned by features, for example. I want to maintain linearity. I won't use neural networks. You get a nonlinear program then. I want to stick to my linear program. That's a subspace parameterized by this phi, the features phi. That's a linear space. Your decision variables are the weights you put on all of these features. So you get a linear program in a more standard sense with a finite number of decision variables. So now my decision variables are parameterized by this alpha, which takes basically linear combinations of the features. It's okay, it's a robust linear program, a finite dimensional robust linear program. You have to, the constraint is parameterized by all x, u, and w. So it's sort of, a robust constraint. The cost involves the moments of the features, and these you can compute. If you go quadratics and stuff like this, the first two moments, for example, you can compute them relatively easily. And then the optimal solution now will depend on C, because I'm doing an approximation. That's a subtle point. Up to now, I can do whatever I want with this measure. It doesn't affect the quality of my approximation. When I go to finite parameterized programs, I have to be careful. And that's a lot of work by Stephen Boyd and also someone in my group about how to choose the C or how to use multiple Cs to get better estimates. Second problem is dealing with the constraints. If you have a model, you can just take the linear program and dualize and try to solve it by robust LP methods. If you don't have a model, you can sample constraints. And that's the simplest thing you can do. You don't need to sample sequential trajectories. You can sample whatever you want. So if you get a bunch of input state transitions from your system for different realizations of the noise, and you get a bunch of measurements, like rewards from your cost function, like in reinforcement learning. You can append arbitrary next actions to them and write, for example, in the deterministic setting, a linear program, vanilla flavor linear program, where you just replace the robust constraint by a sampling of these constraints. And then you can invoke the scenario approach to get guarantees about the optimality, how close you are to optimality to this. Right? That's a very simple vanilla flavor linear program now. And you can solve very big ones of this if you want, for many, many, many samples of your noise. Okay. For stochastic systems, not the end of the story. We still have the expectation to worry about. Two things you can do with an expectation. The one is the sophisticated one. If you can reinitialize the system, do so to your heart's content, collect many samples of the noise, and then use this to form a Monte Carlo estimate of your expectation. And substitute that into your constraint instead of the real expectation. You can invoke concentration bounds and prove things with this, that if you do this and you substitute it back, you get some guarantees of the performance of the system. This is also an unbiased estimator, so no harm done. You can also do a more naive thing, just take any old trajectories, right? Take a bunch of trajectories and then look at the transitions and take averages or more generally linear combinations of these transitions, okay? Then you will get, by taking linear combinations, another transition, a fake transition of your system, which will lead to a biased estimate of any expectations you have, okay? So in principle, there's no reason to expect this would work very well. In general, this doesn't even respect your dynamics. For linear systems, actually it does, and there something interesting happens. If you go to affine systems with quadratic costs, the LP you get by doing this funny mixing of different trajectories they're correlated, so you shouldn't expect to get, you get a biased estimator of your averages, but you still get the right policy. So miraculously, again, you get the wrong linear program, you get the wrong fixed point, but you get the right policy. And that's something about linear quadratic that's sort of magical. Whatever you do to them, it works. Moreover, you can actually generate as many as you want. So if you have some persistence of excitation condition on the data you have collected, you can generate constraints wherever you want and however precise you want them by bootstrapping on the ones you have already. OK, and then I'll wrap up. Just a couple of points. I talked about this linear programming formulation. I didn't talk about the theorems, but you can actually invoke the scenario approach to prove quality approximation for this and how it improves the more samples you extract and how it improves the more precise you make your space of basis functions. You can use this in many different ways. I just talked about the one-shot LP to get the optimal policy, but you can also use for doing policy evaluation. A bit simpler, the feasible set is just a cone, so you can get sample much more effectively. You can add regularization, you can add constraints, you can add auxiliary inputs, you can do whatever you want, right? So you can actually use it in many different ways. You can also try to do iterative schemes for this. It actually works pretty well. One advantage it has over standard reinforcement learning is that it doesn't assimilate the data as it comes in. It has no notion of state. It processes all the data in bulk. So you see, for example, the plots on the top, you're comparing with TD0, a standard reinforcement learning method, and just this is a linear system just doing a least squares fit to the temporal differences, which is basically giving you, on bulk data, giving you exactly the right solution. And you see the method, the LP method is the one, the blue, the one on the bottom, basically converts just a very few samples. On the right, you see an enlargement, a few samples more than the bare minimum you would need to solve a Lyapunov equation, basically. Whereas TD learning just takes forever to converge. And that's sort of, the reason is that it just assimilates the data as it comes in. Also works for nonlinear systems. That's the plot in the bottom. This is for a cart pole system again. Over TD0, huge advantage in terms of the sample efficiency. What the bottom one shows is a little bit of a caveat. If you look on the zoom on the right, there is a little green thing in the end, which is what you get if you don't sample intelligently, if you just sample randomly. And that's one of the drawbacks of what I talked about. If you just sample randomly, you need a lot of data to get even a finite solution to the program. The plot on the top is, as the number of samples increases, what's the fraction of bounded programs you get? And you see you need a lot of samples if your system is big. And the plot on the bottom is the standard thing to do in this case to get a finite program. What we use in our theoretical results as well is just regularize, but then you may bias your solution. So what it's showing is that you actually get the wrong solution if you regularize unless your constraints are rich enough. So basically, there's no free lunch. You have to be smart about how you do your constraints, and that's basically. If you want to know more about this, I'll put the references up. You can look some of these papers.
Hello, everyone. It's a pleasure to be here. I guess I have maybe 10 minutes or so. OK, good. OK, so thanks very much, organizers, for the invitation. OK, I'm just going to skip through the motivation for reinforcement learning because we've seen that. So what I'm going to focus on in this talk is two of the key challenges in RL, which is safety and reward design. So in a lot of RL applications, designing the reward, for example, in autonomous driving or in training large language models or in helicopter flight, is a challenging problem. And so the idea is that we want to learn from an expert and transfer that learning to the new environments. And there are a couple of different frameworks to learning from expert demonstrations. So in the imitation learning, we try to directly learn the expert policy, whereas in the inverse reinforcement learning, we want to learn the reward function that explains the expert policy. And the idea is that this reward function can then be transferred to new environments, new transition kernels, and help us find the optimal policy. And that's the framework that we're going to look at today. And we're also motivated not just by the problems discussed before, but in our lab, we have a couple of interesting problems. We're working, for example, with architects on using robots to build a structure, build a stable structure. And in this case, it's very hard to design rewards for robots to know what should a good structure look like. And also, we have like autonomous cars in the lab and human demonstration, and we try to optimally maneuver these to avoid obstacles, and we want to understand how we can use this to learn the rewards. All right, I think I will directly go to the focus of this talk. So this talk is is based on the work of my PhD student Andreas Schlagenhofen, and it appeared in the ICML last year. And it's about identifiability and generalizability in constrained inverse reinforcement learning. So let me just set up the problem for you. So we have a constrained Markov decision process. I will be very quick because you have seen this. Here we are looking at finite state and action space. P is the transition kernel. Mu is the initial state distribution. And R is the reward. And we have also some constraints. And we also have a convex regularizer. And we are looking in the space of randomized policies to maximize the discounted regularized reward subject to some discounted constraints. Okay. So this problem is fundamentally more challenging than the unconstrained case. For example, deterministic policies are no longer sufficient to characterize the optimal solution. We need randomization. And also the optimal policies are initially condition dependent in general. Also, to look at inverse reinforcement learning, we need this regularizer because without any regularizer, we might get meaningless solutions. For example, any feasible policy, if you choose the reward to be 0, any feasible policy will be optimal on this reward. So that's the motivation for this regularizer. Okay, you also heard about the equivalent linear programming formulation of unconstrained MDP. So here we are, given that the DP in general does not describe this problem, the constraint problem, we're going to look at the linear programming formulation. And we define the state action discounted occupancy measure mu. And using this, we can write the regularized constraint MDP objective as a linear program, okay? So the linear program is in the state of occupancy measures. And there's a one-to-one map between the policies and occupancy measures. And because of that, from now on, we're just going to look at a convex objective where it has the linear part coming from the reinforcement from the reward and a regularizer, and the feasible set is a polytope. And this polytope is given by the feasible occupancy measures. So here, I think the pointer, okay, is E minus gamma P transpose mu is equal to this new initial state distribution is the Bellman flow equation, and then we have this additional linear constraints. And we let f to be a strictly convex function, and we define RL of these constraints f for a given reward to be the set of policies, the policy that is maximizing this objective. And the goal in constraint inverse reinforcement learning is to find the occupancy measure, given an expert occupancy measure to find the reward such that the expert is optimal under this reward. Okay, under the realizability assumption, we can show that the set of rewards that describe an expert policy are exactly the solution set of this min-max problem. Okay. And furthermore, so this is the mean with respect to the reward, max of the with respect to the occupancy measures of our objective function. Okay, and the idea here is that we are minimizing for suboptimality of the expert under a given reward. Okay. And furthermore, under the strict regularization assumption, if now we find the set of rewards and apply or find the optimal occupancy measure corresponding to that set of rewards, we get the expert policy back. So now our goal for the rest of the talk is to characterize this set, so the set of rewards for which the expert is optimal. And we want to do this using convex analytic and linear programming tools. And to also understand whether this goal of under which conditions the goal of IRL, so that the reward we learn will be transferring to new environments. So this, I'm going to skip the proof sketch, and I'm going to go exactly to the questions. So the first question, identifiability. What are the set of rewards that correspond to a given expert policy? Okay. So here we can show that for any constraint and regularization, the set of rewards is a sum of subdifferential of the regularizer and the normal cone at the feasible set of this occupancy measure. Okay, so this is just using convex conjugate duality and the fact that we had a polytopic constraints and we had a convex regularizer. But we can now understand this normal cone a little bit in more detail. So this normal cone is a sum of space of span of E minus gamma P. This comes from the transition kernel, and cone of active constraints at the occupancy measure, active linear constraints. This come from our CMDP formulation and also from the occupancy measure conditions. Okay, so now if we look at this set characterizes all the rewards that are optimal for a given expert. Okay. And all right, so now we can ask the question of, does this set of reward generalize to a new environment? So under which conditions the identified reward can be used to find the optimal policy in a new environment? Okay. And we sort of set the definition of this generalizability. In the past work they discussed this, but there's no sort of concrete definition. And this is the reason we are looking at IRL. We want to find a reward that when we can transfer it to a new environment, we can learn policies that the expert would do. So it's important to ask this question. So to formalize that question, say that let mu E be optimal for some expert reward RE under a nominal transition law and state constraints. Okay. We say that the IRL generalizes to a set of transition law and constraints if for any reward that recover under those nominal ones, if we solve the RL problem, we get the same occupancy measure as the RL problem corresponding to the original reward. Okay. So this is asking, we identify a set of rewards that are that the expert would be acting optimally under these. Now we go to a new transition environment. If we use any of the rewards in this set, do we recover an expert policy in this environment? So our next result exactly answers this question, and it says that to be able to generalize, we have to recover a reward up to a constant shift. Okay, so this is the term on the left-hand side is the set of rewards that we identify under the nominal transition law and constraints, and this condition is saying that we should be able to. This should be a subset of the expert reward plus a constant shift. Okay, so to generalize to new environment, we need to be identifying the reward precisely, but we already in the previous slide, we saw that there is a lot of additional rewards that get identified to an expert. So what can we do about this? So one thing we can do is we can restrict the reward class, okay? So that's one approach. So this is exactly the set that we defined before, the IRL for an unconstrained reward class, and under this polytopic constraints, under the Shannon entropy regularization is the gradient of this regularizer plus the space of the subspace spanned by the transition kernel, and then these additional conic sets that arise because of active inequality constraints. And to be able to, and this in general is strictly contains that RE plus a constant shift. So one way we can address this is restrict the reward class. Okay, I will not talk about the proof sketch, but I'm just going to talk about also sufficient condition for generalizability. And this is, let's say that now we restrict the reward class to a span of certain basis functions. Okay, now we can say that we can uniquely identify the expert reward if a certain rank condition is met. This condition is saying that the space spanned by the potential shape by the transition kernel and the constraint sets does not intersect with the space spanned by our reward class. Okay. And assuming that we know the transition kernel and constraints, we can construct a reward class such that this condition holds. Okay. All right, so maybe just a brief recap of all the things. There's a lot of math symbols on here, but maybe I just give you a brief recap of what we're doing here. So we are looking at a constrained MDP, and we are given an expert policy from which we can get an expert occupancy measure. And we looked at the set of rewards for which this expert is optimal. And this set, using convex analytic tool, we characterize this set as the subdifferential of the regularizer plus additional terms that arise because of the transition kernel, the Blendman flow equation, spanned by these P, and then the conic constraints that arise from the active occupancy measure constraints. Now, we said to be able to take that reward to a new environment and be able to do the same as what the expert would do in this new environment, we need to identify the reward up to a constant, so we can design a reward class such that it doesn't the span doesn't intersect with these spaces, and then we would be able to do that. Okay, I think, so we also looked at finite sample analysis. So in general, in practice, we don't know the expert policy precisely, but we have finitely many data points. And then we looked at, can we bound the suboptimality of the recovered occupancy measure and reward? And I would just briefly talk about these and also show experimental validation on a grid world environment. But just a high-level summary of these in the interest of time. So if we have n samples of the expert's policy and occupancy measure, then we can estimate an empirical occupancy measure. And then if we consider the bounded reward class, we can show the number of samples we need and the length of the trajectory such that we can ensure that the suboptimality of the recovered occupancy measure is bounded by epsilon. And also we can furthermore, assuming that the regularizer is strongly convex, we can bound the suboptimality, bound the distance between the expert policy and the recovered policy. Okay, so coming up with convergent algorithms for IRL is also an active area of research. In this work, we just used the off-the-shelf algorithm, which is based on the Lagrangian and minimax. But in the other works, we also looked at convergence of the algorithms. I would just show briefly experiments on the grid world experiment to kind of highlight some key takeaways. So here is a grid world experiment where the red cells are the constraints and the green are the goal. And here in the under the expert, you see the expert policy shown, and then we consider two reward classes. One of the reward classes, the first one satisfies this rank condition we derived for being able to generalize, and the second one doesn't. and in this case, you can see that under the satisfying this rank condition, we can learn the expert policy better. Good. Okay, I think I just come to summary and outlook. So we formulated constraint IRL problem motivated by the fact that in many, safety is a key problem in RL. To be able to analyze that, we formulated a convex optimization problem, and then using convex analytic tools, we derived a class of rewards that describe an optimal policy. We derive conditions such that this reward, this reward class generalizes to new environments, and provided finite sample analysis where we have only expert data. And so far, we also validated the approach on grid world and compared it with the unconstrained formulation, and also verified the sample complexity and the rank conditions. There's a lot of future directions of work. For example, to make it more realistic, we have to look at infinite state and action setting. In the finite sample setting, we have to look at these notions of approximate generalizability, and that's what we're currently working on. Also, we have looked at learning from multiple experts, so some of these issues with generalizability can be overcome if we have demonstrations from multiple experts, and we're comparing with other methods. Convergence analysis for algorithms that work in IRL, that's an important topic, and also verification on test beds. So with this, I would like to thank you all for your attention. And as I said, this is a joint work with my student, Andreas Schlagnoff. And if you have any questions, please feel free to reach out to me probably after this talk or offline. Thank you very much.